Hello everyone. Welcome back to Golu ki Paathshaala. In part 1 of this chapter, we built a strong foundation by understanding the basics of motion. We learned what motion is, how a reference point helps us describe the position of an object, and why the same object can be in motion for one observer but at rest for another. We also explored the difference between distance and displacement, understood average speed and average velocity, learned about uniform and non-uniform motion, and finally studied acceleration, retardation, and acceleration due to gravity. Now it's time to move one step ahead. In part 2, we'll learn how scientists represent motion using graphs. We'll understand position time graphs and velocity time graphs, learn how to calculate velocity and acceleration using the slope of a graph, find displacement from the area under a velocity time graph, and finally master the equations of motion, which are among the most important concepts for school exams, numericals, and future physics chapters. Don't worry, just like part 1, we'll understand every concept with simple explanations, real-life examples, and easy tricks. So grab your notebook, stay till the end, and let's begin our journey into the graphical world of motion. Let's get started. Graphical representation of motion. Suppose two cars are moving on a road. One is moving at a constant speed, while the other keeps speeding up and slowing down. Now imagine trying to compare their motion just by looking at a table full of numbers. Sounds difficult, right? That's exactly why we use graphs. Graphs are one of the simplest and most effective ways to represent motion. They help us understand how the position, velocity, or acceleration of an object changes with time in a clear and visual way. With the help of graphs, we can easily compare the motion of different objects, identify whether the motion is uniform or non-uniform, and even calculate important physical quantities like velocity, acceleration, and displacement. In this chapter, we'll learn how to draw and interpret graphs that show the relationship between position and time and velocity and time. Before we begin, here's one important point to remember. All the graphs we'll study in this chapter are for motion in a straight line and in one direction only. This means that distance is equal to the magnitude of displacement, and speed is equal to the magnitude of velocity. Also, if an object starts from zero position at zero time, then the position time graph is the same as the distance time graph, and the velocity time graph is the same as the speed time graph. Now that we've understood the basics, let's begin with our first graph, the position time graph. Now that we know what a position time graph is, let's learn how to draw one step by step. Don't worry. It's much easier than it looks. Let's take an example. Suppose a vehicle is moving on a straight road. Its position is recorded every second. At 0 seconds, the position is 0 meters. At 1 second, it's 20 meters. At 2 seconds, 40 meters. At 3 seconds, 60 meters, and so on until 6 seconds, where the vehicle reaches 120 meters. Our goal is to represent this information on a graph. Step 1. Take a graph paper. Draw two lines perpendicular to each other. Their point of intersection is called the origin, represented by O. The horizontal line is called the x-axis, and the vertical line is called the y-axis. Step 2. Decide what each axis will represent. Since we want to see how the position changes with time, we'll plot time on the x-axis and position on the y-axis. Step 3. Choose a suitable scale. For this example, we can take 5 small divisions equals 1 second on the x-axis. 5 small divisions equals 20 meters on the y-axis. This helps us use the graph paper neatly and accurately. Step 4. Start plotting the points. The first point is 0, 0, so we'll mark it at the origin. Next, at 1 second, the position is 20 meters. Locate 1 second on the x-axis and 20 meters on the y-axis. The point where these two meet is your second point. Similarly, plot the remaining points, 2, 40, 3, 60, 4, 80, 5, 100, 6, 120. Finally, join all the plotted points. You'll notice that they form a straight line. This straight line is called the position time graph for this motion. Since the graph is a straight line, it tells us that the vehicle is covering equal distances in equal intervals of time. In other words, the vehicle is moving with uniform motion. And don't forget, this same method can also be used to draw other graphs that we'll study later in this chapter, such as the velocity time graph. Great! We've learned how to draw a position time graph. But now comes the real question. What can this graph actually tell us? Well, a position time graph is much more than just a line on a graph paper. It tells us how the position of an object changes with time and helps us understand the nature of its motion. Let's look at two different types of position time graphs. Case 1, straight line graph. Suppose the position time graph is a straight line. What does this mean? It means that the object is covering equal distances in equal intervals of time. For example, if the object travels 20 meters between 2 and 3 seconds, and again 20 meters between 5 and 6 seconds, then its velocity remains the same throughout the journey. Since the velocity is constant, the object is said to be moving with uniform motion or constant velocity. So, here's an easy trick to remember. Straight line equals constant velocity equals uniform motion. Now let's move to the second case. Case 2, curved graph. What if the graph is curved instead of straight? A curved graph tells us that the object is not covering equal distances in equal intervals of time. For example, between 4 and 6 seconds, it may travel a shorter distance, but between 10 and 12 seconds, it covers a much larger distance. This means the object's velocity is changing with time. And whenever velocity changes, the object is said to be in accelerated motion. So, remember this second trick. Curved graph is equals to changing velocity is equals to accelerated motion. That's why, just by looking at the shape of a position time graph, we can quickly identify whether an object is moving with constant velocity or accelerated motion. In short, straight line means constant velocity, that is uniform motion. Curved line means changing velocity, that is accelerated motion. Isn't that amazing? A single graph can tell us so much about an object's motion. So far, we've learned how to draw a position time graph and how its shape tells us whether an object is moving with constant or changing velocity. But here's something even more interesting. Can a position time graph tell us the velocity of an object? The answer is yes. A position time graph doesn't just show where an object is at different times. It also helps us calculate how fast the object's position is changing, which is nothing but its velocity. Let's see how. Suppose we choose any 2 points on the graph, say A and B. Point A represents the object's position S1 at time t1, and point B represents its position S2 at time t2. Now, draw a horizontal line from point A and a vertical line from point B. This forms a right-angled triangle. In this triangle, the vertical side represents the change in position, that is S2 minus S1. The horizontal side represents the change in time, that is T2 minus T1. Now remember the formula for average velocity? Average velocity equals change in position divided by change in time, so we simply divide the change in position by the change in time. For example, if the object moves from 40 meters to 80 meters in 2 seconds, then average velocity equals 80 minus 40 divided by 4 minus 2 is equal to 40 divided by 2, that is 20 meters. Simple, isn't it? Now here's the most important concept. The ratio of the change in position to the change in time is called the slope of the graph. In simple words, the slope tells us how steep the graph is. And in a position time graph, the slope represents the velocity of the object. So, remember this golden rule: slope of a position time graph equals velocity. If the graph is steeper, the object is moving faster. If the graph is less steep, the object is moving slower. So, by simply looking at the slope of a position time graph, we can compare the velocities of different objects without doing lengthy calculations. In the next topic, we'll use this concept again while studying the velocity time graph, where the slope helps us find another very important quantity, acceleration. Now that we've understood the position time graph, let's move on to another very important graph in physics, the velocity time graph. As the name suggests, a velocity time graph shows how the velocity of an object changes with time. Just like the position time graph, here also we'll plot time on the x-axis. But instead of position, we'll plot velocity on the y-axis. Now, let's understand 3 different cases. Case 1, constant velocity. Imagine a car moving on a straight highway at a constant speed of 20 meters. Since its velocity remains the same every second, the graph will be a straight horizontal line, parallel to the x-axis. This means the velocity is not changing with time. And remember, acceleration is the rate of change of velocity. So, if the velocity isn't changing, the acceleration is 0. So here's our first memory trick: horizontal line, constant velocity, 0 acceleration. Simple, right? Case 2, increasing velocity. Now imagine another car that starts from rest and keeps moving faster every second. For example, its velocity increases by the same amount in equal intervals of time. In this case, the graph becomes a straight line sloping upward. This tells us that the car is speeding up at a constant rate. In other words, the car has constant positive acceleration, and the acceleration is in the same direction as the velocity. So remember, upward sloping line, increasing velocity, constant positive acceleration. Case 3. Decreasing velocity. Now let's look at the opposite situation. Suppose a car is moving with a velocity of 15 meters, but it starts slowing down. Its velocity decreases by equal amounts in equal intervals of time. This time, the graph is still a straight line, but it slopes downward. This means the object is slowing down with constant acceleration acting opposite to the direction of motion. We also call this negative acceleration or retardation. So here's the third memory trick: downward sloping line, decreasing velocity, constant negative acceleration. Let's quickly revise all three graphs. Horizontal line means velocity remains constant, that is, acceleration equal to 0. Upward sloping line means velocity increases, that is, constant positive acceleration. Downward sloping line means velocity decreases, that is, constant negative acceleration or retardation. By simply looking at the shape of a velocity time graph, we can easily understand whether an object is moving at a constant speed, speeding up, or slowing down. In the next topic, we'll discover something really interesting. We'll learn how a velocity time graph can help us calculate acceleration and even displacement, using just its slope and the area under the graph. We've just learned how different velocity time graphs help us understand the motion of an object. But here's an interesting question. Can a velocity time graph tell us anything more than just the velocity? The answer is yes. In fact, a velocity time graph helps us find two very important physical quantities: acceleration and displacement. Let's understand them one by one. First, finding acceleration using the slope. Do you remember what we learned from the position time graph? The slope of a position time graph gives us velocity. Similarly, in a velocity time graph, the slope tells us the acceleration. Think about it. The graph shows velocity on the y-axis and time on the x-axis. So, the slope simply means change in velocity divided by change in time, and that's exactly the formula for acceleration. Acceleration is equal to change in velocity divided by change in time. Suppose at 10 seconds, the velocity is 5 meters, and at 20 seconds, it becomes 10 meters. The change in velocity is 5 meters, and the change in time is 10 seconds. So, acceleration equals 5 divided by 10 equals 0.5 meters square. This means the object's velocity is increasing by 0.5 meters every second. Now imagine the opposite situation. If the velocity decreases from 10 meters to 5 meters in the same time interval, then the acceleration becomes minus 0.5 meters square. The minus sign tells us that the object is slowing down. This is called negative acceleration or retardation. So here's a simple rule to remember. Slope of a velocity time graph equals acceleration. Second, finding displacement using the area under the graph. Now let's learn something even more interesting. The area enclosed between the velocity time graph and the time axis gives us the displacement of the object. Yes, just by finding the area, we can calculate how far the object has moved. Let's understand this with a simple example. Imagine the graph is a horizontal line, which means the object is moving with constant velocity. The area under the graph forms a rectangle. And what is the area of a rectangle? Length into breadth. Here, length represents time, breadth represents velocity, so area is equal to velocity multiplied by time. But we already know that when velocity is constant, displacement is equal to velocity multiplied by time, so the area under the graph is equal to the displacement. For example, if the velocity is 20 meters for 6 seconds, then displacement equals 20 times 6 equals 120 meters. Simple. Now suppose the velocity is increasing with time. In that case, the area under the graph is no longer just a rectangle. Instead, it consists of a rectangle and a triangle. To find the displacement, we simply calculate the area of both shapes and add them together. Displacement equals area of rectangle joड़ area of triangle. Quick revision. Let's quickly remember the two most important results of a velocity time graph. Slope of the graph is equal to acceleration and area under the graph is equal to displacement. These are two of the most frequently asked concepts in school exams, numericals, and even higher classes. So make sure you remember them well. Now that we've learned how graphs help us calculate acceleration and displacement, we are finally ready to study the equations of motion, which connect all these quantities together and make solving numericals much easier. So far, we've learned about motion, velocity, acceleration, position time graphs, and velocity time graphs. Now it's time to learn one of the most important topics of this chapter, the kinematic equations of motion. These equations are extremely useful because they help us solve numericals quickly and predict the motion of an object without drawing graphs every time. Before we begin, let's understand one important condition. These equations are valid only when an object is moving in a straight line with constant acceleration. If the acceleration keeps changing, these equations cannot be used. Now, there are 5 physical quantities involved in the motion of an object. The first is displacement, represented by s. The second is initial velocity, represented by u. This is the velocity of the object before the motion begins. The third is final velocity, represented by v. This is the velocity after a certain time. The fourth is acceleration, represented by a. And finally, the fifth quantity is time, represented by t. The kinematic equations simply establish a relationship between these 5 quantities. Let's derive them one by one. First kinematic equation. We already know that acceleration is defined as the change in velocity divided by the time taken. So, acceleration equals final velocity minus initial velocity, whole divided by time. Replacing the symbols, we get a equals v minus u by t. Now, multiplying both sides by t, at equal to v minus u. Finally, bringing u to the other side, v equals u plus at. This is called the first kinematic equation. It helps us calculate the final velocity of an object when the initial velocity, acceleration, and time are known. Now let's move to the second kinematic equation. Do you remember what we learned from the velocity time graph? The area under the velocity time graph gives the displacement. For an object moving with constant acceleration, the area under the graph consists of a rectangle and a triangle. So, displacement equals area of rectangle plus area of triangle. After substituting the values and simplifying the expression, we get our second equation. S is equal ut plus half at square. This equation helps us calculate the displacement of an object when the initial velocity, acceleration, and time are known. Now let's derive the third kinematic equation. Sometimes, we need to solve a problem where the time is not given. In such situations, we combine the first and second equations and eliminate the time variable. After simplifying the equation mathematically, we obtain v square is equal to u square plus 2as. This is called the third kinematic equation. It is especially useful when time is unknown but displacement is given. So, let's quickly revise all 3 equations. First equation, v is equal to u plus at. Second equation, s is equal to ut plus half at square. Third equation, v square is equal to u square plus 2as. These 3 equations are known as the kinematic equations of motion. Together, they relate the 5 important quantities of motion: displacement, initial velocity, final velocity, acceleration, and time. One important point to remember is that these equations are valid only when the acceleration is constant. Also, if the object is moving only in one direction, then the distance traveled is equal to the magnitude of displacement, and the speed is equal to the magnitude of velocity. However, if the object changes its direction during motion, then the signs of displacement, velocity, and acceleration become very important because they indicate the direction of motion. These equations form the foundation of physics and will be used repeatedly in higher classes as well. So make sure you understand not only the formulas but also when and how to use them. Until now, we've been studying motion in a straight line, where an object moves only in one direction. But in real life, not every object moves like that. Think about a car overtaking another vehicle, a football being kicked into the air, or a satellite revolving around the earth. Do all these objects move in a straight line? No, they move in different directions, forming curved paths. This type of motion is called motion in a plane, or two-dimensional motion. In two-dimensional motion, an object moves along both the length and the width of a plane. In simple words, its direction keeps changing as it moves. One very common example of motion in a plane is circular motion. As the name suggests, when an object moves along a circular path, its motion is called circular motion. Let's understand this with an example. Imagine a child sitting on a merry-go-round in a playground. As the merry-go-round rotates, the child moves along a circular path. Suppose the child starts from point A, moves through point B, and reaches point C. Now let's answer two important questions. First, what is the distance traveled by the child? Distance is the total length of the path covered. So, in this case, the distance is the curved path from A to B to C. Now, what is the displacement? Displacement is the shortest distance between the initial and final positions. So here, it is the straight line joining point A and point C. Notice something important. The curved path is longer than the straight line. This means that in circular motion, the distance traveled and the displacement are generally not equal. Now let's consider a complete revolution. Suppose the child completes one full round and comes back to the starting point. What will be the distance traveled? The child has traveled one complete circumference of the circle. And we know that the circumference of a circle is 2 pi r, where r is the radius of the circle. So, the distance traveled in one complete revolution is 2 pi r. Now here's an interesting question. What is the displacement after one complete revolution? Think for a moment. The child starts from one point and returns to the same point. Since the initial and final positions are the same, the displacement is zero. This is a very important concept and is often asked in examinations. Now suppose the child takes t seconds to complete one revolution. The average speed is equal to the total distance traveled divided by the total time taken. So, average speed is equal to 2 pi r divided by t. But what about the average velocity? Since the displacement is zero, the average velocity is also zero. So remember this important point. After one complete revolution, distance equals 2 pi r, displacement equals 0. Average speed equals 2 pi r divided by t, average velocity equals 0. Now let's move to a special type of circular motion called uniform circular motion. When an object moves along a circular path with a constant speed, its motion is called uniform circular motion. Notice the words, constant speed. This means the object covers equal distances in equal intervals of time. But does that mean its velocity is also constant? The answer is no. Remember, velocity depends on both speed and direction. Even though the speed remains constant, the direction of motion keeps changing at every instant as the object moves around the circle. And whenever the direction of velocity changes, the velocity itself changes. Let's understand this with another example. Imagine an athlete running around a rectangular track. The athlete runs with the same speed but changes direction only at the four corners. Now imagine the athlete running on a hexagonal track. This time, the athlete changes direction 6 times in one complete round. Now keep increasing the number of sides of the track. As the number of sides becomes larger and larger, the shape gradually becomes a circle. In a circular track, there are no corners. Instead, the direction changes continuously at every point. That's why, in uniform circular motion, the speed remains constant, but the velocity keeps changing continuously because its direction is constantly changing. So let's quickly revise. Motion in a plane is motion in 2 dimensions. Circular motion is the motion of an object along a circular path. In one complete revolution, distance traveled is equal to 2 pi r, displacement is 0, average speed is equal to 2 pi r divided by t, and average velocity is 0. Finally, in uniform circular motion, the speed remains constant, but the velocity changes continuously because the direction of motion keeps changing. This is one of the most important concepts of the chapter, so make sure you understand the difference between speed and velocity before moving ahead. Now let's perform a simple and interesting activity to understand one of the most important concepts of circular motion. Take a ring, such as an empty adhesive tape ring, and place it flat on a smooth surface. Now put a marble inside the ring and gently roll it so that it moves along the inner boundary of the ring in a circular path. Observe the marble carefully as it keeps moving around the ring. Now here's the question. What do you think will happen if we suddenly lift the ring while the marble is still moving? Will the marble continue moving in a circle? Or will it move in some other direction? Let's find out. After the marble completes 1 or 2 rounds, carefully lift the ring without disturbing its motion. You'll notice something interesting. The marble does not continue moving in a circular path. Instead, it immediately moves in a straight line. But why does this happen? The ring was forcing the marble to move in a circular path. As soon as the ring is removed, that force is no longer present. So, the marble continues moving in the same direction in which it was traveling at that exact instant. This direction is called the tangent to the circle. A tangent is a straight line that touches a circle at only one point. At every point on a circular path, the velocity of the object is always directed along this tangent. In simple words, if an object moving in a circle is suddenly released, it will move along the tangent at the point where it is released. Now let's connect this idea with uniform circular motion. Earlier, we learned that acceleration is produced whenever velocity changes. Many students think that since the speed is constant in uniform circular motion, the acceleration must be zero. But that's not correct. Remember, velocity depends on two things, speed and direction. In uniform circular motion, the speed remains constant, but the direction changes continuously at every instant. And whenever the direction of velocity changes, the velocity also changes. Since the velocity is changing continuously, the object is continuously accelerating, even though its speed remains the same. This is why uniform circular motion is called an accelerated motion. Finally, it's important to remember that perfect uniform circular motion is an ideal situation. In the real world, it is difficult to maintain exactly the same speed while moving along a perfectly circular path. However, this model helps us understand many real-life situations, such as the motion of planets around the Sun, satellites revolving around the Earth, and vehicles taking circular turns on roads. With this, we complete one of the most important concepts of this chapter. You now know that in uniform circular motion, the speed remains constant, but the velocity keeps changing because its direction changes continuously, and therefore, the object is always accelerating. Before we end this video, let's do a quick revision of everything we've learned in part 2. We started with the graphical representation of motion and learned how graphs help us understand motion visually. Then, we studied the position time graph and velocity time graph, learned how to interpret them, and understood that the slope helps us calculate velocity and acceleration, while the area under the velocity time graph gives displacement. Next, we learned the three kinematic equations of motion and saw how they relate displacement, velocity, acceleration, and time for motion with constant acceleration. Finally, we explored motion in a plane and uniform circular motion, where we understood circular motion, distance and displacement in one revolution, and why an object moving with constant speed in a circle is still considered to be accelerating because its direction keeps changing. And with that, we've successfully completed part 2 of chapter 4, describing motion around us. Keep revising these concepts regularly, and you'll be able to solve both theory questions and numericals with confidence. Now let's quickly revise the entire chapter with the help of this mind map. The chapter begins with the basic concept of motion, where we learned about reference point, position, motion, and rest. Next, we understood the difference between distance and displacement, followed by the concepts of average speed, uniform motion, non-uniform motion, average velocity, and acceleration, including positive acceleration, negative acceleration, and acceleration due to gravity. After that, we studied the graphical representation of motion. Here, we learned about the position time graph and the velocity time graph, how to plot them, how to interpret them, and how the slope and the area under the graph help us calculate important physical quantities like velocity, acceleration, and displacement. Then, we moved on to the kinematic equations of motion, where we learned the three equations used to relate displacement, velocity, acceleration, and time for motion with constant acceleration. Finally, we explored motion in a plane and uniform circular motion. We understood the concepts of circular motion, distance and displacement in one complete revolution, average speed, average velocity, tangent to a circle, and why uniform circular motion is considered an accelerated motion even though the speed remains constant. And that's the complete journey of chapter 4, describing motion around us. If you found this video helpful, don't forget to give it a big thumbs up, share it with your friends, and subscribe to Golu ki Paathshaala for more easy and interesting CBSE science videos. Press the bell icon so you never miss our upcoming lessons. Thank you so much for watching.